In this section, we'll compare autoregressive and masked language models. The goal is to build an intuitive picture of how they're trained, what architectural trade-offs they make, and where each one fits in real-world LLM systems. We'll also connect that to careers by looking at the kinds of knowledge and practical judgment hiring teams usually expect when they interview for LLM and applied AI roles. At the heart of modern language models is one key training choice, and it shapes everything that follows. A causal language model learns by predicting the next token using only the words that came before. A masked language model works differently. It fills in missing tokens using context from both directions. That single split influences the model's architecture, the kinds of tasks it fits best, the tools around it, and even what teams look for when hiring. Here's the key difference in how the two objectives work. In a causal language model, the model reads tokens in order and uses only the previous ones to predict the next token, which is the GPT-style setup. In a masked language model, one token is hidden, and the model uses both left and right context to fill it in, which is the BERT-style setup. That attention constraint largely determines what each model does best. Autoregressive models are designed for generation. They work by taking the previous tokens from x1 through xt-1 and predicting the next token, xt, using left-only attention and moving one step at a time. A flagship example is GPT-3, a 175 billion parameter language model evaluated in few-shot, one-shot, and zero-shot settings. In Hugging Face, this setup is handled with AutoModelForCausalLM, where inputs are shifted to serve as labels. Masked language models are built to understand context by hiding some tokens and asking the model to predict them from both the left and the right. That bidirectional setup helps them learn rich language representations from unlabeled text. BERT and Roberta are the classic examples. In Hugging Face, AutoModelForMaskedLM supports this setup, including fill masked inference and the token corruption used during training. The key difference here is structural. A causal mask forces the model to move left to right, which makes it well suited for generating coherent text over time. Full attention works differently. Every token can use information from the entire sequence, which is much better for understanding and interpretation. That's why attention patterns aren't interchangeable. You can't just swap them and expect the model to stay equally good at the same task. Here's a quick task-to-model fit summary. For chat coding copilot and agent planning, causal GPT-style models work best because they generate one token at a time and handle continuation and step-by-step reasoning naturally. For classification, named entity recognition, and semantic search or reranking, masked BERT-style models are usually stronger since they use full bidirectional context to produce richer embeddings and more accurate token-level understanding. This slide shows the data flow for training a causal language model. We start with raw text, tokenize it, and then create inputs and labels from the same sequence by shifting the labels one position forward. At each step, the model sees the previous tokens and learns to predict the next one. Because training is set up this way, text generation becomes the model's natural inference behavior. Here's the masked language modeling training pipeline. We start with raw text, tokenize it, and then randomly mask about 15% of the tokens. The model's job is to predict those hidden tokens from the surrounding context. That masking step creates the training signal. Because there's no causal left-to-right constraint, the model can use the full sequence, which helps it learn rich contextual representations rather than just next-word prediction. In production, these two components work as a pipeline. First, the user sends a query. A masked encoder turns that query into an embedding and uses it to retrieve the most relevant documents or context. Then the causal generator takes both the query and the retrieved information and composes a clear, coherent response. So together, retrieval finds the right knowledge, and generation turns it into the final answer the user sees. Yes, BERT can generate text, but there's an important caveat. The ACL paper BERT has a mouth and it must speak showed that if you treat BERT as a Markov random field language model, it can produce fluent, varied text. The trade-off is that it generally falls short of left-to-right models in overall generation quality. So for long, coherent token-by-token generation, causal models are usually the more natural choice. This slide connects skills to career paths. For LLM or agent engineering, the focus is causal language model fine-tuning, prompting, inference optimization, and strong evaluation pipelines. Search, ranking, and NLP roles lean more on masked encoder fine-tuning, embeddings, retrieval, and token-level tasks. And in applied ML or AI product work, success often comes from choosing the right model for each subproblem and designing hybrid systems that balance generation with representation. Here's the key tooling split in Hugging Face. Both causal and masked language modeling use the same trainer API, but the setup is fundamentally different. For causal LM, the model predicts the next token, so labels are just the input shifted by one. For masked LM, labels are the original tokens hidden during corruption. That affects attention masking, label handling, and inference behavior, and ultimately determines what kinds of products you can actually build. For portfolio projects, build something that makes the contrast obvious. A strong example is a side-by-side benchmark. Fine-tune a small causal model for text continuation and a masked model for classification on the same corpus. Then explain the wins, failures, and how the training objective drives those results. Another great project is a hybrid RAG pipeline, using a masked encoder for retrieval and a causal model for answer generation. Here are 4 interview questions worth mastering. First, left-to-right attention means each token can only look at earlier tokens, which preserves causal generation. Second, bidirectional context helps masked models because they use both left and right context to build stronger token representations. Third, know the Hugging Face classes, AutoModelForCausalLM for generation, and AutoModelForMaskedLM for fill-in-the-blank style objectives. Finally, be ready to discuss evaluation, from task metrics and human review to F1 and retrieval recall. Model selection judgment is where many hiring loops get most critical. 2 common misses show up fast. First, recommending a masked model for a long-form chatbot, which ignores that chat requires generation. Second, defaulting to a causal model for every understanding task. Even when an encoder is more efficient, the strong signal is matching the model family to the product need, latency constraints, and a clear evaluation plan. Here's the guiding rule for model choice. Start by asking one simple question. Are we generating text or understanding text? If the product's job is to produce the next words, we use a causal model. If the job is to analyze, classify, or interpret text, we use a masked model. And if it's a hybrid product, we use both, each in the role it's best suited for. Here's a realistic way to prioritize the path. First, build a strong foundation. Understand both objectives at a conceptual level and know how they show up in Hugging Face tooling. Next, for applied ML or product roles, be able to explain generation versus representation trade-offs clearly. Then, if you're targeting LLM or agent engineering, go deeper on causal fine-tuning, prompting, inference, and how to evaluate generated outputs effectively. Here's the core mental model to remember. Autoregressive models are trained to keep continuing text, while masked models are trained to fill in missing text using both left and right context. That one difference drives how the models behave, which tasks they're best at, the APIs and tools around them, and even what interviewers look for. If you can explain, build, and justify both, You're showing real model selection judgment. So the big takeaways are pretty simple. Start with the objective. Causal models are built to generate, while masked models are better for understanding. So the choice should follow the business problem. Then know the tooling well enough to explain what's happening under the hood, like attention masking, label shifting, or token corruption. And finally, show your work. A benchmark or hybrid pipeline is what really demonstrates practical, production-ready judgment.